Hello everyone and welcome to this video where we are discussing the memory map of the chapter Thermodynamics. Now the first question that might be plaguing you is what exactly is thermodynamics? Now thermodynamics is nothing but the exchange of heat and work between a system and its surroundings. So the next obvious question is what exactly is a system and what counts as a surrounding? A system could be anything. It could be as simple as a pizza on table. Now in this case, the pizza is the system that you are studying and everything around it, that is the surroundings, the air, the beach, everything is the surroundings. But a system could actually be anything and a surrounding may not always be the open air. For example, if I place this pizza in an oven and I start studying the pizza inside this oven, then in this case the pizza is still the system and now the oven in totality is the surroundings. So don't always think that surroundings means open air and the environment. It could simply be anything that is not the system. So anything that is not the system is counted as the surroundings. In this case, the pizza is the system and the microwave is the surroundings. The first thing that I want to talk about now with respect to thermodynamics is the idea of thermodynamic equilibrium. Now, to understand thermodynamic equilibrium, we must ask the question that what are the different values that we need to perfectly describe any thermodynamic system. For example, in case of a gas, the system is completely described if you can say the values of pressure, volume, temperature, mass and the composition. If I give you these values, then that system which is made up of a gas is completely describable. So thermodynamic variables are those variables which are needed to completely describe a system. And if the values of these systems do not change, then we say that a thermodynamic system is in equilibrium. So let me define thermodynamic equilibrium formally. A thermodynamic system is said to be in thermodynamic equilibrium when macroscopic variables such as pressure, volume or temperature for a gas which characterize the system do not change with time. So remember, the thermodynamic equilibrium is defined by macroscopic variables. These are variables which are dependent on the bulk properties and not the microscopic properties. So here, if these variables don't change values in time, then the system is said to be in thermodynamic equilibrium. The next thing that we will talk about is thermal equilibrium and the zeroth law. To understand this, let's consider three systems which are in contact with each other. Here we have three systems A, B and C, and you will see carefully that there is a wall that separates each of them. The wall or the partition between A and B is such that no heat can pass between these systems. However, the wall that separates A and C or B and C is such that heat is allowed to pass between them. Also remember that overall the box is insulated, which means that heat cannot escape from the box or enter it. So the entire box is insulated. Now this means that the systems can only interact with each other. That is, A can interact with C and B can interact with C. However, A and B cannot interact with each other. If you allow this system to be observed in time, you will see that heat energy will start to flow from A to C given that the temperature of A is greater than the temperature of C. And due to this, the internal energy of C will start to increase. Let's say that the temperature of A was T1 and the temperature of C was T3. After some time, it will be observed that no heat energy is flowing, which means that A and C will have some common property between them, because of which the heat energy has stopped flowing, and we know that this common property is nothing but temperature. And this is nothing but thermal equilibrium. The condition that the temperature of the system, which in case is A, matches the temperature of the surrounding, which is nothing but the system C, is known as thermal equilibrium. So A was our system and we said that C is the surrounding because A is the system we were studying. So now A and C are in thermal equilibrium because their temperatures are the same. A similar conclusion can be drawn between B and C because the heat energy from B will also start flowing into C because T2 is also greater than T3. After some time again, B and C will attain the same final temperatures. However, remember that A and B have not been allowed to act. Heat has only flown from A to C or B to C. Now B and C are also at the same final temperature. So now let me ask you a question. If next I remove the partition between A and B, that is, if I remove the partition which was not allowing heat to flow and replace it with a partition that allows heat to flow between them, what exactly do you think will happen? Even though now the partition between A and B can flow heat between it, no heat will be observed to flow from A and B. Why exactly does that happen? This exactly defines the zeroth law. Zeroth law says that all bodies in thermal equilibrium must have a common temperature. We already saw that A and C had reached thermal equilibrium, and so had B and C, which would automatically mean that A and B were also in thermal equilibrium. So if A and C have a common temperature and B and C have a common temperature, then A and B also will have the same temperature, and this is the zeroth law of thermodynamics. The next thing that I want to talk about is the internal energy of the system. The internal energy by definition is the sum of the molecular kinetic and potential energies, which means you must find out the kinetic and potential energy of every single molecule and add them all up, and this will give you the internal energy. Internal energy is given by the letter capital U, and this is a sum of UK plus UP. However, under the study of kinetic theory of gases, which you will learn shortly in the next chapter, you will see that the interaction between the molecules is completely ignored. Because this interaction is very poor, we completely neglect the potential energy of the internal molecular forces, and therefore UP is completely ignored, which means we will say that the internal energy is only due to the kinetic energy of the molecules. But even in kinetic energy, there are three aspects. The first one is the translational kinetic energy, the second one is the rotational kinetic energy, and the third one is the vibrational kinetic energy, and therefore the internal energy is a sum of these three types of kinetic energies. So U is equal to UT plus UR plus UV. Now I also want to talk about what exactly changes the internal energy in a system. Now internal energy depends only on the state of the system and does not depend on the path which you take to reach that state, and because of this the internal energy is known as a state variable. So what exactly will change the internal energy? Whatever changes the state of the system will change the internal energy, because internal energy depends only on the state. So the next question is, what is changing the state of a system? And the answer is that heat and work done on a system will change the state of a system. So we say that heat and work in thermodynamics are not state variables, they are actually just modes of energy transfer so that a system can change its internal energy. So the next question is, how do heat and work change the state of a system? So we said that heat and work can change the internal energy of a system, and that means that when you apply heat to a system or you take away heat from the system, you must be changing the values of the macroscopic variables. For example, if you supply heat to a gas, it might expand and go from one set of PVT to another set of PVT. In the same way, you can also do work on a gas. If you push this piston downwards, you will see that it is changing the values from one set of PVT to another set of PVT. In both these cases, that is whether you exchange heat or you exchange work with the system, you have caused a change in the state of the system and hence caused a change in the internal energy. Now, the relationship between the heat, work and the internal energy of a system is known as the first law of thermodynamics, and it simply says that delta Q is equal to delta U plus delta W. Now, this is a very wonderful and fundamental law of thermodynamics. It is basically saying that any heat energy exchanged in a system might be converted either in a change in its internal energy or in a change in its work. So if you can track how much heat energy has gone in and out of a system, you can get the summation of the change in internal energy and the change in work done. So let's see what formula can be used to find out each of these parts of this equation. If you're talking about finding out the change in the heat energy of a system, you can use the formula for the change in temperature, that is Q is equal to mc delta T. But it could also be that heat energy is exchanged due to a change of state, in which case you will use the formula Q is equal to mL, where L is the latent heat. But what about the internal energy? We have already seen that the internal energy is nothing but a sum of the kinetic and potential energies of a system. But we also saw that for an ideal gas, you say that UP is equal to 0, which means we must remember the formula only for UK. And UK is nothing but 3 by 2 nRT, where R is the gas constant and T is the temperature. From this I will get that delta U, which is the change in internal energy, is 3 by 2 nR delta T, where delta T is the change in temperature. So I've given you the formulas to find the change in heat, and I've given you the formula to find the change in internal energy. But what about the formula for work done? To answer this question, we first have to ask, what is the work done by an ideal gas? Now, normally to understand the work done by an ideal gas, we take a system that looks exactly like this. We take a beaker in which is our system, that is the ideal gas, which is the red molecules that you can see. This beaker is fitted with a piston, and initially we say that the cross-sectional area of this piston is A, and the pressure of the system, that is the pressure of the gas, is capital P. Now, because of the pressure of the gas might push the piston and the piston might come above. And because of this, we say that the gas is exercising a force, that is exerting a force on the piston. And this force will be nothing but the pressure of the gas multiplied by the area of cross section of the piston, as we know from the definition of pressure. So force is equal to pressure into area, and I say that the force is PA. Now, once I know the force that is exerted on the piston, the next question I can ask is, what is the distance that this piston has moved, and we'll call this distance delta x. Now, it's very simple to write down what is the work done. The work done by the gas will be nothing but the force exerted multiplied by the distance through which the piston moved, that is F into delta x. However, F we said is P into A, and therefore I can say that the work done is P, A into delta x, which is nothing but the change in volume that was experienced when this gas moved upward. So there was a change in volume occupied by the gas, which is delta V, and from here we get the answer that the change in work, or the work done by an ideal gas, is equal to pressure times the change in volume. So W is equal to P delta V. There's one other way in which you can find out the work done by a gas. You can do this if you plot the values of pressure and volume on a graph known as the PV graph. For example, this gas initially had a volume of V1, and after expansion it reached a volume of V2. If you keep in mind the values of pressure and volume and plot them on a graph which we call as the PV graph, then from the area under the curve of such a graph, you can find the work done by the gas. So in this case, that is the expansion of this gas, we would get a curve that looks something like this, and then to find the work done, you simply find the area under the curve, which is nothing but the integration of P dV, going from the initial volume V1 to the final volume V2, and this is the area that the curve and the x-axis have trapped between them. So this gives you the work done by an ideal gas. So from the understanding that work done is equal to the area under the PV curve, let's try to write down the values for the work done for some other types of PV curves. For example, if I have a curve which is parallel to the x-axis, in such a case the area under the curve will simply be that of a rectangle. And then I'll simply find the area by doing length into breadth, which is nothing but P into V2 minus V1. And therefore the work done by this gas will be P1 multiplied by V2 minus V1, which is the area of this rectangle. What if I had a curve that looks something like this? In this case, where I have a straight line which is parallel to the y-axis, there is no area that is trapped between this curve and the x-axis, and therefore the work done in this case will come out to be 0. We can also take a look at a different kind of a PV graph. In this case, you have a straight line which is inclined to the x-axis, and now the area trapped between this line and the x-axis will be something like a trapezium. And we know the area of a trapezium is half into the sum of its parallel sides into height. The sum of the parallel sides will be nothing but P1 plus P2, and the height is V2 minus V1, and therefore work done by this gas will come out to be half P1 plus P2 into V2 minus V1. So now let's see if we have really understood what kind of variables the internal energy, work and heat are. Let me give you an example. Let's say that I am taking a system from a point A where it had some set of values P1, V1 and T1 to a different state of the system that is at point D on the PV graph, that is, it is having a value P2, V2 and T2. Now I want to take this system from A to D, and I can take it in two separate ways. I can take it from A to B and then from B to D, but I can also take it in a different way where I take it first from A to C and then go from C to D. So now I'm saying that I can go from point A, that is the first state of the system, to point D, which is the second state or the final state of the system, in two separate ways. That is, I can first take path 1, which I will call as ABD. So I can take path 1, or I can take path 2. In path 2, I will follow the path AC to CD, and this is path 2. Now let me ask you the question, are the values of Q, W and U the same for both the paths, or are they different? Now let's write that down. For path 1, we will see that the value of the heat energy will be Q1, the value of work is W1, and internal energy is simply U. However, if I take a look at part 2, I will see that the heat energy that has been exchanged in this part will be different, so I say it's Q2, and the work done is also different, so it will be W2, but the internal energy transfer in this part is exactly the same. And this exactly tells me that heat energy changes depending upon which path you take to go from one state to another, and similarly work done also changes depending upon the path, but the internal energy does not change, as you can see. And therefore I say that work and heat depend upon the path taking, whereas the internal energy depends only on the initial and final states, which is exactly the definition of a state variable. Finally, let me give you some sign conventions when you are trying to use the first law of thermodynamics. If the heat is supplied to a system, then in such a case, the delta Q is said to be positive. However, if heat is drawn from the system, delta Q is negative. If the system is undergoing an expansion, then in such a case, delta W is positive. However, if the system is compressed, in such a case, delta W is said to be negative. Finally, if there is an increase in temperature, then the internal energy increases and therefore delta U is positive. However, if the temperature is dropping, then delta U is negative because the temperature decreases and so does the internal energy. Now, the next important question to ask is what information is needed to be able to reproduce a system, that is to make a copy of the system. To understand this, let's take an example. Here I have a cylinder, let's say an oxygen cylinder, and it's written that the volume of the cylinder is 14.4 liters. Now, this cylinder is being filled with oxygen at a certain temperature and at a certain pressure. Now, in order to make a copy of this system, I will take another oxygen cylinder which has the same volume because it has the same shape, and I will also fill oxygen inside this at the same temperature, same pressure, and of course it has the same volume. Now what I'm trying to tell you is that in this case I can guarantee that for an ideal gas, for the same values of pressure, volume and temperature, both systems will have the exact same number of moles. All I had to do was make sure that both of them had the same pressure, same volume at the same temperature, and I was guaranteed that the number of moles in both of them was going to be exactly the same. And therefore these variables which can define the set of properties of a system which we can use to make a copy, such variables are known as thermodynamic variables. In this case, for an ideal gas, pressure, volume, temperature and the number of moles are enough to describe the system completely, and they are the thermodynamic variables. And the relationship between these variables is what we call as the equation of state, and that is PV is equal to nRT, where P is pressure, V is volume, N is number of moles, R is the universal gas constant, and T is the temperature. Now once we have the relationship between these variables, let's also define what are the types of variables. There are two important types of variables, extensive and intensive variables. Variables whose values change with the size of the system are known as extensive variables. For example, if you take a small part of a system and write down the values for its volume, mass and internal energy, and then look at a different part of the system and write down the values, you will see that these values are changing from one part of the system to another. Specifically speaking, two volumes can be added to give the whole volume. That is, I can add the volume of all the parts of the system to give the total volume of the system, and therefore these values are telling us about the size of the system. On the other hand, if I have a certain different type of variables, for example variables like temperature, pressure or density, then it doesn't matter which part of the system I am looking at, whether I am looking at a small part, whether I am looking at a big part, whether I am looking on the left or the right, it doesn't matter. These values are not changing, and therefore you can say that these are intensive variables. They don't vary with the size of the system. In general, if you want to check whether something is intensive or extensive, check if you can add it depending upon the size. You can't add the temperature of one half of the system to the other half of the system and say that the whole system has T1 plus T2 temperature. But you can do that with the volume and the mass. So volume and mass in this case would be extensive variables, whereas temperature or density would be intensive variables. Now we know the relationship between heat, work and internal energy for a thermodynamic process, but there are a large number of thermodynamic processes in nature. There are some certain types of special processes that we will first study. The first type of special process is a quasi-static process. A quasi-static process by definition is a process in which all parameters remain in equilibrium at any given instant. So it is an ideal infinitely slow process. So this means that in a quasi-static process, at any given point in the process, the system is always going to be in equilibrium. Why do we do this? Let me give you an example. Let's say that we have this system and here we have placed a large number of weights on the piston, and because of the weight of these different weights, we can see that the gas is kept at a fixed volume. The initial values of the thermodynamic variables, let's call them P1, V1 and T1, are represented on the PV graph at point I, which stands for the initial state. Now what if I suddenly remove the weight from this piston? In such a case, if the weight is suddenly removed, the gas will undergo a sudden expansion and the values of pressure, volume and temperature will undergo a large number of changes till they settle upon the final values P2, V2 and T2. The problem with such a process is that I'd have no information about all the values of pressure, volume and temperature that took place between the initial and final point. All of the states that the system went through between I and F are known as non-equilibrium states, and we have no definite picture about their values. To avoid this, what we do is we set up a quasi-static process. To understand this, let's take that example again. Again, initially the gas has state variables of values P1, V1 and T1. And now, instead of removing a large number of weights, we remove small amount of weights one by one. I removed one weight and the system went from P1, V1, T1 to the new values, which will bring it to the point A on the PV graph. Again now I wait till the system reaches an equilibrium state and write down these new values. After it has reached an equilibrium state at A, now I will remove a small weight again and allow the system to go to B. In this way, I will make the system go from P1, V1, T1 to P2, V2, T2, but not all at once. I will make it go through a large number of equilibrium states by going step by step from point I to point F. Because of this, I have a knowledge of all the values that are present for the system between points I and F. And this is what we mean by a quasi-static process. All the processes that we will deal with in this chapter by default quasi-static processes unless stated otherwise. Next we come to what is known as an isothermal process. In an isothermal process, the temperature of the system does not change and hence we can say that delta T is equal to 0. In this case, what could happen is that let's say that a gas is expanding. If the gas expands, then we know that on expansion, the temperature of the gas might reduce because it loses heat energy to the surroundings. However, even though the gas loses heat energy to the surroundings, it will be placed in contact with a reservoir which will give it back the heat energy it loses in such a way that the temperature of the system does not change. An isothermal process is depicted by an isotherm, which is just the PV graph as shown in the diagram. This is isothermal expansion. Exactly the opposite thing will take place if I am trying to do isothermal compression. While I compress the gas, I expect that heat energy from the surroundings will enter my system and cause the temperature to rise. But my system will be in contact with a sink and therefore all the extra heat energy will be absorbed by the sink, which is a reservoir, and therefore the temperature of my system will not change. Again, delta T will be 0. For an isothermal process, because delta T is 0, delta U will come out to be 0 because delta U depends directly on delta T. And because delta U is 0, from the first law of thermodynamics, I can say that delta Q will be equal to delta W. Also keep in mind that for an isothermal process, the specific heat will come out to be infinity. We also know from equation of state that PV is equal to nRT, and therefore if temperature is not changing, it means that the right-hand side nRT are all constant for a given number of moles, and therefore PV will also be a constant. And finally, also remember that the coefficient of isothermal elasticity will be equal to pressure for an isothermal process. We can also write down the formula for the work done in an isothermal process. It will be given as W is equal to nRT ln V2 by V1, where n is the number of moles, R is the universal gas constant, T is the temperature, ln is the log to the base e, and V1 and V2 are the initial and final volumes of the system respectively. The next type of process that we will study is the adiabatic process. In such a process, there is no heat exchange between a system and its surroundings. For example, if you have tea that is placed inside an ideal thermos flask, it means that this flask will not allow heat to be exchanged between the hot tea inside, and therefore no heat can go from inside to outside, nor can any heat enter from the outside to the inside. This is an example of a system where no heat is exchanged within the system and the surroundings. Now, because delta Q is equal to 0 in an adiabatic process, now we can draw a PV diagram for the adiabatic process, and it looks something like this. Now, we know that delta Q for an adiabatic process is 0. Because of this, from the first law of thermodynamics, we can say that delta U will come out to be minus delta W, which means that if the work done is positive, then the change in internal energy will be negative, and vice versa. Two main conditions are required for setting up adiabatic processes. First one is that restrict heat exchange, that is, there should be complete thermal insulation. But there is also one other important factor, that is, the process should take place so quickly that there should be no time for heat exchange between the system and the surroundings. Finally, also remember that an adiabatic process connects two isothermal processes. So here, if you are given two isothermal processes like the red and the yellow lines, then you can connect it by an adiabatic process, that is the white line. For an ideal gas in an adiabatic process, the equation can be written as PV raised to gamma is equal to constant, where gamma is the ratio of the specific heat capacities at constant pressure and constant volume. We can also find the work done in an adiabatic process by finding the area under the PV curve, and it will be given as W is equal to P2V2 minus P1V1 upon 1 minus gamma. The next type of process is the isobaric process. In an isobaric process, the pressure of the system remains constant throughout, which means that if I try to draw a PV graph, then at volume V1 I will get a point which has a pressure P1, but at a later time when the system has a volume V2, we will still be at the same pressure P1, and hence the graph of an isobaric process is simply a straight line parallel to the x-axis, and therefore the area under such a curve will come out to be a rectangle, giving me the work done for an isobaric process to be equal to P1 V2 minus V1. In an isochoric process, the volume of the system remains constant, and therefore delta V is equal to 0. In such a case, there will be no area under the curve, and therefore we say that the work done is 0. But because the work done is 0 from the first law of thermodynamics, we can also say that delta Q is equal to delta U. Finally, we also talk about polytropic processes. In fact, the polytropic process is just a general way of describing all the processes that we have seen. The equation for a polytropic process is PV raised to n is constant. If you put n is equal to 1, you will see that this is nothing but PV equal to constant, which is nothing but an isothermal process. If the value of n is gamma, then we will see that this becomes PV raised to gamma, which is equal to nothing but the adiabatic process. Similarly, if n is equal to 0, then I get P is a constant, which is nothing but the isobaric process, and if n is infinity, then I get V is a constant, which is nothing but the isochoric process. And thus the polytropic process is just a general way of describing all the processes that we have seen. Finally, let's also discuss what are known as cyclic processes and non-cyclic processes. In a cyclic process, the initial and the final states of the system are exactly the same. That is, the system returns to its initial state after any number of changes. Because of this, the change in the internal energy of the system will be 0. This is because the initial and final states are the same, and therefore the initial and final internal energy will be the same, so delta U will be 0. And therefore delta Q is equal to delta W for all cyclic processes. We must also remember that the work done in any process is given by the area under the curve, but because these are closed curves, the work done will be nothing but the area enclosed by these curves. It is also important to note that if the cycle is anti-clockwise, then the work done comes out to be negative, whereas if the cycle is clockwise, then the work done comes out to be positive. Finally, non-cyclic processes are those in which the final and initial states of the system are different. These are the types of processes that we are studying in this chapter. So we learned about cyclic processes, but where exactly do we use this idea of cyclic processes? We use it in a system called as a heat engine. In fact, a heat engine is nothing but a device in which a system is made to undergo a cyclic process that results in the conversion of heat to work. In fact, if you take a look at the history of thermodynamics, then its roots lie in the study of heat engines. So what exactly goes in the making of a heat engine? Now, every heat engine has something what is known as a working substance. For example, fuel vapor and air is the working substance of a diesel engine, whereas steam is the working substance of a steam engine. So every heat engine has a working substance. This working substance absorbs heat from an external reservoir. Now let's say that it absorbs heat Q1 from an external reservoir at a high temperature T1. So we say that the working substance is taking heat from a source at T1, and then this working substance rejects or releases heat to another external reservoir at a lower temperature. So let's say that the heat rejected by this working substance is Q2 and it is rejecting it to an external reservoir at a lower temperature, that is at temperature T2. Now, what is the point of this? I am taking heat at a higher temperature and I am releasing heat at a lower temperature. The idea is to ask, what is happening to the heat that you are keeping with yourself? The system is taking Q1 but giving out Q2. So what is it doing with the heat Q1 minus Q2? And this difference is actually what is converted into work. So the difference in the heat received versus the heat released, this difference is converted into work by the engine. And to convert it into work, you will attach this part of the engine to an external arrangement for where you want the work to be output. So for example, you could connect this to a piston, you could connect this to a lever that you want to pull, you could connect it to a wheel, and at this point where the work output is coming from the engine, that is the heat energy difference, will be converted into work and your wheel will turn or your lever will move or your piston will be pressed, etc. So let's take a look at the working of this heat engine one more time. For example, if you can see in this given system, you have the working substance which is absorbing heat energy from a source at temperature T1, where T1 is a high temperature, and let's say that the heat absorbed by this working substance is equal to Q1. Once this working substance absorbs the heat energy Q1, let's say that the working substance may be a gas, and then this gas will expand and move through the pipe where it reaches the chamber of the piston. And therefore the heat energy is traveling to the chamber where the piston resides, and because the gas now has heat energy, it will push the piston and cause the piston to move, which will cause the wheels to turn, and therefore at this position where the piston is attached, you will see that the work is being transferred from the heat engine to the outside. So this is the portion where we are getting work from the heat engine. However, it will not use all of the heat energy that it is absorbed to push the piston. Some of it will be released back into the system, and this heat energy which will be released back is Q2, which will go back into the sink at a lower temperature T2. And therefore I will say that according to first law of thermodynamics, over one complete cycle, the work that I will receive from the heat engine is W is equal to Q1 minus Q2. So the heat engine is doing nothing but using the difference in the heat energy it takes and the heat energy it releases. It uses this difference to do some amount of work. Now all heat engines are characterized by their efficiencies. By definition, the efficiency of a heat engine is given as eta is equal to W upon Q1, where Q1 is the input heat energy and W is the work done. But we saw that the work done is nothing but Q1 minus Q2, and therefore I get that eta is equal to Q1 minus Q2 upon Q1, which I can also write as 1 minus Q2 by Q1. Now remember, I can also see that if no heat is rejected by the system, that is, if it uses all the energy that is absorbed to do work, then I will get no heat rejection, that is Q2 will be 0, and in such a case eta will be 1, which means that the efficiency of the engine is 100%. And if a heat engine is 100% efficient, then it means that it is converting all of the heat energy that it is absorbing into work. However, in practice, it is impossible to find a heat engine that converts all heat into work, which means that for all practical reasons, eta is always less than 1. That is, the efficiency of any heat engine in the entire world will always be less than 100%. So the next question that is obvious to ask is, what is the maximum possible efficiency that I can get from a heat engine? And the answer to this is that the most efficient type of heat engine is what is known as a CARNOT engine. A CARNOT engine is nothing but a reversible engine operating between two temperatures. And it can achieve this maximum possible efficiency by undergoing what is known as the CARNOT cycle. So what exactly is the CARNOT cycle? The CARNOT cycle is a cyclic process which is made up of 4 stages. The system undergoes a process where it goes from A to B, B to C, C to D, and then back to A. A CARNOT cycle consists of 2 isotherms and 2 adiabats, and together we get the CARNOT cycle, which gives the maximum possible efficiency of a heat engine. So a CARNOT engine has the highest efficiency for a given temperature range. And finally, let's define what is the efficiency of the CARNOT engine. The efficiency of the CARNOT engine is eta is equal to 1 minus T2 by T1, and therefore it depends upon the temperatures between which the engine is operating. Finally, we can also say that Q1 upon T1 is equal to Q2 upon T2 for a CARNOT engine. In case of a heat engine, the heat engine was absorbing heat at a high temperature, giving out heat at a low temperature, and using the difference in these energies to give out work to the environment. In a refrigerator, exactly the reverse happens. So a refrigerator is the reverse of a heat engine. What it does is now absorbs or extracts heat at a low temperature, gives out heat at a high temperature, and instead of giving out work to the environment, we actually have to do work on the refrigerator. And therefore, for a refrigerator, we say that work is done on the machine and not obtained from it. The principle of the refrigerator and the heat pump is the same. Let's quickly see what are the characteristics of a refrigerator. Just like the heat engine, the refrigerator also has a working substance. However, now heat is extracted from a reservoir at low temperature. So the amount of heat extracted is called Q2 and the temperature of the reservoir is T2. After this, the refrigerator then releases heat, which is Q1, at higher temperature, that is at T1. So it is taking heat at low temperature and giving out heat at higher temperature. Now, is this a normal process? Absolutely not. It is going to take a lot of effort to take out heat from a system that is already cold, because we are taking from a low temperature system. So it's going to take a lot of effort to take out heat from a reservoir which is at lower temperature, and therefore we say that work has to be done onto the system. And where will this work done be shown onto the diagram? You will see that in the diagram the work done will be there in the portion of the blue arrow, and this work done will be the difference between the heat energy. So take a look at what is happening. In this system, Q1 is the output of the system, that is Q1 is going out from the working substance, whereas Q2 is going into the work substance, and the work done is also going into the working substance, and therefore Q2 and W are inputs to the working substance, whereas Q1 is an output that is going out from the working substance. You will see that inside the refrigerator we have 2 different types of coils. One is the white coil and the other is the green coil. We also have 2 devices. One is an expansion device and the other is a compressor. Now, in a refrigerator, the working substance, which is usually in a gaseous form, goes through the following steps. First, there will be a sudden expansion of the gas from high to low pressure because of the expansion device. This cools this gas and converts it into a vapor-liquid mixture. After this coil fluid will absorb the heat from whatever region it has to cool. For example, it will take away the heat from the food that we are trying to preserve and convert it into vapor. Finally, the vapor is then heated due to external work in the compression device, and therefore because of this external work, the vapor is heated rapidly. This heat is then released by the vapor to the surroundings, where it passes through the green coils, which will release this heat to the nearby surroundings and bring it back to the initial state and complete the cyclic process. Just like the heat engine, the coefficient of performance of a refrigerator must also be measured. The formula for the coefficient of performance is the heat extracted divided by the work done, which is nothing but Q2 by W. In case of a refrigerator, Q2 was the heat that was input to the working substance, and we also did work on it, and therefore W plus Q2 is the total amount that was input to the working system, whereas Q1 was the heat rejected by the working substance, and therefore it's on the other side. But from this we can say that W is equal to Q1 minus Q2, and therefore the coefficient of performance comes out to be Q2 upon Q1 minus Q2. Finally, now I can see that the best kind of refrigerators will be those in which I don't have to do any work, and therefore I can see that the best kind of refrigerators would be those in which transferring heat from the cold to the hot body was possible without any external work being done on it. And therefore, the best refrigerator would be that for which W is equal to 0. And if W is equal to 0, then Q1 would be equal to Q2 and beta would then become infinity. And these would be the most ideal refrigerators in existence. Now, just like 100% efficient heat engines do not exist, similarly refrigerators with infinite coefficients of performance also do not exist. But what is stopping these devices from existing, even though they are not in the violation of the first law of thermodynamics? And what is stopping them is the second law of thermodynamics. The second law of thermodynamics is a principle which disallows certain phenomena consistent with the first law of thermodynamics, and this is the second law of thermodynamics, which in its essence says this. The second law says that the level of disorder in the universe is steadily increasing, and systems tend to move from ordered behavior to more random behavior. Now that sounds pretty vague. We'll define it in just a moment, but what I also want to tell you is that can be said in a different way. Kelvin Planck's statement from the second law of thermodynamics says that it is impossible to make an engine which converts heat energy completely into mechanical energy, and therefore the second law of thermodynamics explicitly forbids 100% efficient engines. So from this idea, we have to first ask, how do I even measure what is the order of a system? To measure the order of a system, we define what is known as entropy. By definition, it is the measure of the randomness or disorder of the molecules of a system. And we just saw that the system must always move towards disorder. That's the second law of thermodynamics. The formula for entropy, that is delta S, is equal to Q subscript REV divided by T, where QREV is nothing but the heat exchanged in a reversible process divided by the absolute temperature. From the ideas of second law of thermodynamics and entropy, we will begin to define two essential types of processes. The first one is a reversible process. A reversible process is nothing but a process in which we can, if we wanted to, change the system and the surroundings back to their original states with no other change in the universe. In a reversible process, what happens is that the change in entropy comes out to be 0. There is no net change in entropy. However, in an irreversible process, entropy always increases. So the change in entropy is always positive, and the total entropy of the universe is continuously increasing. And this is the same thing as the second law of thermodynamics. Second law said that disorder is increasing. Instead of disorder, we are calling it entropy, and now saying that entropy is always increasing. And entropy always increases in which kind of process? The irreversible process, which means that in nature it must be obvious that irreversible processes must be more common. So I asked the question, why is the idea of reversibility so important? First of all, we already saw that for maximum efficiency of a heat engine, the processes need to be reversible. Secondly, all engines based on irreversible processes have lower efficiencies. And finally, like I said, reversibility idea is important because in nature, irreversibility is the rule and not the exception. Most natural processes are irreversible and not reversible. So this completes all the different concepts that I want to revise with you in thermodynamics. I hope you found this chapter as interesting as I find it. Thank you for watching. So thank you for watching another memory map. We work very hard to bring these memory maps to you. Please subscribe to our channel by clicking on this button and tell your friends to subscribe as well. If you want to buy your very own target book, you can also click on this button. Keep watching for another video from our channel.